start the recording. All right. So collisions. All right. So let's get into this collisions. All right. So remember that what we looked at, right? We're gonna be looking at three different general scenarios. Right. The first scenario, right, is really elastic, right? We're gonna be looking at elastic collisions, right? So let's look at that. The first scenario would be elastic. Second scenario would be inelastic, actually. Let me fix that. And you guys are familiar with these, right? Inelastic. Alright, so we have these. So these different ones, right? So we looked at Newton's first law, Newton's second law, Newton's third law, right? So looked at all of those, right? And the conservation of momentum. So we're going to be looking at this now. Elastic collisions. What would be elastic collisions? What are elastic collisions? What do we speak about when we talk about elastic collisions?
When there's rebound after collision.
Repeat.
When there is rebound after collision.
So rebound. All right. So rebound, recoil. Both objects moving off. All right. So we have two bodies, basically, right? So two bodies. It can be two or more. Really, it can be two or more bodies, right? So when they're going to be colliding, right? So two or more bodies collide and move off. Right? That's what we're looking at. Without losing energy, right? Move off separately, right? Without losing any energy. Right? So I would say that, right? I could also add without losing any energy during collision. To be specific, right? So we're saying what we're saying here, is that not only is momentum conserved, but energy is also conserved, kinetic energy. All right. So that's what we're having there. Inelastic collisions. Now, what happens in inelastic collisions? What happens there?
Silent energy.
Not only that, but the bodies collide. Then what?
They move off in the same direction.
No. Right? That's perfectly inelastic, but inelastic, right? So both bodies collide. I wouldn't say and that doesn't make any sense, right? then separate, right? So they collide, then separate after collision, right? But what happens here, is that momentum is conserved, right? But kinetic energy isn't. So momentum, right? So not kinetic energy. I have the urge of just writing K. Alright, so we have that there. For perfectly not inelastic. No, these are special cases, always special. Perfectly inelastic. The thing is now for inelastic collisions, right? Let's say that the objects actually move off. The objects can actually move off together in some certain cases, right? But if the kinetic energy isn't conserved, then it's still inelastic, right? But not perfectly inelastic, right? In perfectly inelastic, right? We have both objects moving off together, right? So the bodies collide as we stated, right? Move off together, right? So you could say that they stick together and then move off together. All right. So we could look at this. The collision is inelastic, right? So momentum is conserved, but in kinetic energy shouldn't be, right? So looking at this here, it shouldn't be. There are cases in which you like calculate it and then kinetic energy is conserved and stuff like that, right? But if it is conserved, then we would generally say that it is elastic, right? If they stick together and move off, right, we can say that it is behaving as a perfectly inelastic collision, but when we identify the kinetic energy before and after, then it behaves elastic, right? So you're gonna have to like describe the situation, right? Describe it from the view of momentum, right? And then describe it from the view of kinetic energy, right? But generally, right, let me just put this here. So generally, right, momentum is conserved and kinetic energy is not. Generally, right? So generally it is. All right. So what I want to look at, right, is a first case, right? We're just gonna be doing two. Well, we're gonna be doing questions, and then I'm gonna send you guys a table, all right? And then we'll move on from there, all right? So first example, example number one, right? So I want you guys to just. We're probably just gonna work through it regardless, right? So what we're saying, two billiard balls. You guys know what a billiard ball is, right? Right? I'm just gonna be writing this. Are there any questions that you guys have for me while I just write this down? You know what? I'm not gonna write this down. I'm gonna send it to the group and then we're gonna do the question because in the interest of time, let's just do that. All right. So let me send the question to the group, the WhatsApp group, and then we'll just do it. I have the question here. Let me just bam and send it. Alright, so guys, just look in the WhatsApp group for this question, and we'll do these questions and then get out of here. The Angular thing, we might just do that tomorrow instead of doing questions. We might just do that. Because since we do practice questions in the class already, then not really a big deal. So we're doing that exercise 1, and we're also doing exercise 2. So I want us to read that question or those questions, and then let's go from there. All right. So question 1, right? Can everybody see it in the WhatsApp group?
Yes.
All right. So working from there, two billiard balls or billiard rather balls, right? Collide. Ball 1 moves at a velocity of 4 meters per second, and ball 2 is at rest. After collision, ball 1 comes to a complete stop. What is the velocity of ball 2 after collision? Is this collision elastic or inelastic? Right? The mass of each ball is 0.16 kilograms. So what are we doing here, right? So let's write down what we have. For ball 1, what do we know about ball 1? So the mass of ball 1, m, is equal to 0.16 kilograms. What's the velocity of ball 1? The initial velocity of ball 1 is 4 meters per second, right? The final velocity of ball 1 is 0 meters per second because it came to a rest. Can you guys appreciate that? You're seeing what's happening, right?
Yes, sir.
Alright, so let me just fix these because they look like 5s. Alright, so we have that there. For ball 2, we're saying that ball 2 is the same mass. Initial velocity of ball 2, u is equal, so u is equal to 0 meters per second, right? And then the final velocity is v x, or what we just call a question mark. It's just x, we don't know what it is, right? So let's just call this v2, v1, call this mass 2, call this mass 1. So that's there. Are we okay with this concept? Are we okay with these values that we have here? It would be delightful if I received an answer. Alright, hold on, let me just check to make sure that
Yes,
you're there.
sir.
Alright, lovely. Alright, let me just join back the meeting. You know, I'm not gonna join back the meeting in my phone. I just need you guys to like speak to me. Alright, so if there's something in the chat, just let me know. Alright, so let's work off of this. So what do we have here now? What are we trying to find? The final velocity of ball 2, right? Or what we call V2. Okay. So what do we know here? What could we use? We know that momentum is conserved, yes? In all collisions. Yes, momentum is conserved in all collisions. So let's recall the law of conservation of momentum, right? Remember total momentum, total initial momentum rather, is equal to total final momentum. Alright, we have that there. So this is fine. And we can write that mathematically, right, as m1u1 plus m2u2 is equal to m2u2 plus m2v2, right? So I have that there. Let's plug these values in now. Right, we end up with 0.16 kilograms times 4 meters per second. I have that there plus 0.16 kilograms, right, times 0 meters per second. That is the initial momentum of 1 and 2. And we have the final momentum of 1 and 2 now. This is times 0 meters per second. And then we add now the final momentum for 2 which would be 0.16 kilograms times V2. All right, so can we appreciate this? Is this understood?
Yes, sir.
All right, so what's the answer now? On one side of the equation, what we end up with 0.16 times 4 is what? 0.64 plus 0, which is equal to 0 plus 0.16 V2. Yes? So we end up with 0.64. Technically we'll just write kilograms meters per second. Okay, let's just write that kilogram meters per second is equal to 0.16 V2 divided by 0.16, divide this by 0.16, and this is 4 meters per second. V2 is equal to 4 meters per second. Lovely. All right, so that's fine.
Yes, sir.
All right, so how do we determine whether or not the collision is elastic or inelastic?
Checking the kinetic energy.
All right, so we must check the kinetic energy. What is the formula for kinetic energy? K is equal to
Half mv squared.
half mv squared. Lovely. Moving on. Right, therefore, we're going to have half m1 u1 squared plus half m1 v1 squared. Sorry, that is wrong. That is so wrong. Lies, lies. 2 u2 squared is equal to now half m1 u1 squared plus half m2 v2. Okay, so this should be v2 squared. All right. So what are we getting for this now? I want you guys to work these, All right, done. So what's happening here now? Is this elastic or inelastic? Is this elastic?
Sir,
Elastic.
It is elastic because kinetic energy is conserved. It is elastic. Oh my gosh. Embarrassing. Alright, hold on. I was about to write isalic, right? Elastic. Alright, lovely. There's another question, but in the interest of time kind of gone. Do you want to do the question or you can just do that on your own? You can do, I mean, it's literally, no, it's not the same thing. You want to do that question and then go? And then tomorrow we do the angular stuff?
yes, sir.
Alright,
Yes, sir.
so let's do example 2 or practice question number 2. Alright, so I want you guys to just go and read the question while I get this thing to work because, yeah. I'm guessing my screen stopped sharing.
Yes.
Yes, sir.
Yes, it did. All right, give me a moment. But just read the question. You know what? Do the question. Do it right now, right? And then we'll go through it. Let's have a go at that question, all right? Let me know when you're finished, and then we'll go through it. All right. So are we done with the question yet?
No, sir.
No, no, I'm not done yet. But it's fine. And we know that there's a different equation, right? Just saying. It's not the equation that we use up here. That's a wrong equation. Wrong, 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 wrong. So we need a different equation for it. Equation for perfectly inelastic collisions. That's what we need to use. And you can derive it though, it should be fine. Just derive that. As physicists, we can derive anything. Alright, so giving you guys a couple more seconds to just try to complete that. And then we head into it. And with the power of friendship, we can defeat the question. Alright, hold on. The time of life. 1 more minute. Alrighty. So let's have a look at this question and let's get into it. Alright. The question says that an object A has a mass of 2 kilograms, moving at an initial velocity of 3 meters per second, and collides head on with object B, which has a mass of 1 kilogram, right? Moving in the opposite direction, with a velocity, initial velocity of 4 meters per second. After collision, both objects stick together so that they move with a common velocity v. Calculate that common velocity v. All right, so we have this M2U2. So just a question: who noticed that the 4 meters per second should be negative?
Me.
Okay, lovely. Not the me. All right, so yeah, 4 meters per second should be negative. Lovely, moving in opposite direction, right? So we end up using total momentum before collision and total momentum after collision, right? After we end up with m1 u1 plus m2 u2 is equal to, because after collision, right, we have A and B sticking together. We have the combined masses of m1 and m2 and a common velocity v. All right. So we end up with 2 kg plus 3 meters per second squared. Well, sorry, not plus. That would be times. Looking for the momentum, mass times velocity. Right. So we have that plus 1 kg times 4 meters per second is now equal. Alright, so let me just give it a second, give the screen a second to like update. It's gonna be equal to 2 kilograms plus 1 kilogram times V. This is gonna be 6 plus what? Or is it minus rather? This should be negative 4. My bad, let me fix that. Times negative 4. I look at negative 41. Let me fix that as well. Negative 4. Alright. What we have here, is that what we got? Is that what everybody has? Hold on, what's happening? Hmm, my brain is lapsing, you know. It's lapsing. Alright, let me just do everything on the calculator then. The answer, V, is gonna be equal to, hold on, what's happening? V is gonna be equal to 0.67 meters per second. Did everybody get that? 0.67 meters per second?
Yes, sir.
Alright. Alright, lovely. It's really 0.6 repeating, or 0.6 repeating, and this is meters per second square, but we don't use the repeating value though that much. I use the repeating value because the lecturer can't tell me nothing, but right, that is, oh, we have 0.6, it would be 0.6666666 going off as a irrational value. So what we did was just we rationalized it, right, basically by rounding off to make it 0.67. All right, but that is all we have for today.